All right, we'll move to the next topic, which is on that theme of infrastructure-supported autonomy. So I, over the weekend, was having fun with AI image generator in DALL-E, and I typed up this prompt here, describing my idea for depot autonomy, and I told AI to imagine what this would look like, and that's what it came up with, which I actually thought was a pretty cool image. But I'm going to be starting the presentation, and Seth, who's one of our roboticists working on this, is going to finish up the second half of the presentation with some of the technical work that we're doing. Infrastructure-supported autonomy. The basic idea here is infrastructure investment is happening. It's happening for reasons beyond autonomy, right? It's happening for public safety reasons. It's happening for business efficiency reasons. It's happening for security systems and public safety. So the world is getting more sensors and more compute in the infrastructure. It's already there. It's already paid for other reasons. How can we use that to make autonomy in mobility better? And the specific case of depot autonomy is within a constrained operational design domain, like a warehouse, that has a fence around it. Is there a way that we could take like an L2, level 2 vehicle, like think of the Amazon Rivian vehicles that have cameras and radars already on them? Could we make that vehicle operate autonomously at level 4 in a depot environment if we leveraged cameras and LiDARs in the infrastructure and some compute? Sort of like, think of an analogy to like air traffic control, but sort of vehicle traffic control within a depot. So here's the sort of toy version of the model, right? Where it's, you've got your depot, your warehouse, it's inside a fence line. So we don't have to worry about the safety case of the general public wandering in, right? Everybody's an employee, everybody's been trained, they're all wearing safety vests. Vans come in, they're empty because, they just dropped off all their packages on their delivery run, and they got to go through loading, charging, cleaning, inspection, repair, and then go, wait for a human to take them out and do the rest of the package delivery route. So here's my elevator pitch for why we're doing this, because there's been a couple things that have made autonomy roll out slowly. One of them that we talk a lot about, and Henry's published on this, is the curse of rarity, right? That it's just a really tough technical problem because there's a lot of long tail issues that need to be handled. Another curse is the curse of a lack of a business case, right? And that's a big one, right? Because there really aren't that many good business cases out there for autonomy. There's a lot of people who know how to lose billions of dollars in autonomy. Not a lot of people who know how to make money. So this is an idea on how to make money, depot autonomy. And this is my elevator pitch, which is actually 2 slides long. So I need it to be a really tall building with a very slow elevator. But the first slide is sort of the business side. So if you think about warehouse space, it's growing rapidly. Everybody wants everything just in time, right? We want to order our Amazon thing in the morning and have it delivered in the afternoon, right? So the whole area of warehouse and just-in-time delivery is really taking off. Warehouse work, the biggest constraint in warehouse work that constrains their efficiency is they can't get enough humans to do the work. And the reason for that is it's not good work for humans. A lot of people get hurt. It's really strenuous work. They quit because it's boring, repetitive work. It turns out to be very good work for automation, right? That's why this space, warehouse autonomy generally, is really proceeding very quickly. And there's a lot of investment interest. So total addressable market is increasing dramatically. We figured out how, and I'm working with teams in the Ross Business School to validate this, that we have a positive business case. And the positive business case in this case comes from reuse of existing equipment to keep costs down, right? So on the vehicles, we say the vehicles are like those Rivian vans. They've already got the compute on the vehicles. They've got the sensors on the vehicles. They've got the actuation on the vehicles. We're just reusing that in a different way. Warehouses already have a lot of monitoring systems and a lot of logistics optimization systems. So they have sensors in the infrastructure. They have compute. So, we're making this whole sort of just-in-time package delivery ecosystem, much more efficient to, potentially generate more revenue by delivering more packages more efficiently. And we're doing it with moderate costs because we're reusing existing infrastructure to keep the investment costs down. So here's more sort of the technical approach part of the pitch, which is that, we've worked very hard to keep our scope technologically feasible, right? We've not tried to take on, unbounded technical problems like some of the people in the AV space have. And the way we've kept it bounded is, one, we've kept it low speed, right? All these vehicles moving through the warehouse are moving very low speed. So low kinetic energy. So less severity if accidents happen because of low kinetic energy. Plus occurrence rates are lower just because things happen slower, right? The pedestrian has more time to get out of the way because vehicles are moving slowly. Chaos is minimized because, it's a warehouse. We got a security system, right? Everybody in the warehouse is trained. It's indoors, so there's good lighting. There's no bad weather. Security keeps out the general public, right? So technologically, when we think about all the hazards that can occur and how do we, put in place countermeasures for them, we've, put in place an operational design domain that is fairly technically feasible. The other thing that's interesting about our approach is it's actually unique in the industry. Nobody else is doing this, what's called Type 3 or vehicle plus infrastructure solution. People are either doing a complete vehicle-only solution like a Waymo, where you put all the intelligence in the vehicle does everything with no support from the infrastructure, or you do the Type 2, the infrastructure-centric, which is sort of like what Bosch did at the Stuttgart airport, where all the smarts and all the sensing is in the parking garage itself, and the parking garage controls the vehicles moving through the parking garage, and they act as sort of like blind followers of the infrastructure guidance. We are doing a more optimal partitioning where we're saying the things that infrastructure is better at, and I'll show this on the next slide, we allocate those to the infrastructure, and the things the vehicle's better at, we allocate those to the vehicle. Now, why are we the only ones doing this Type 3 approach? Because it's more complicated, right? Companies in the AV space where you have safety critical failure modes, they want to own everything, right? One company wants to be in control of everything. Like Bosch wants to control the entire system, so they do infrastructure only. Or Waymo wants to control everything, so they put everything on the vehicle, right? But this is a more optimal approach. Everybody's aiming at that. And we as Mcity should be working on the next thing that everybody's aiming at, right? So that's why we're working in this space. And there is a continuing need for partners and sponsors in this work. So the call to action in my elevator pitch is, if you want to get involved, we'd love involvement. Please reach out. So now let's talk about that. The Type 1, Type 2, the vehicle-centric, infrastructure-centric, and the middle one, which is the middle column is what we're doing. So just think about all the different tasks you have to do in a depot autonomy system, right? Like the vehicle comes in, it's got to get a map of the depot, it's got to get a mission plan, and it's got to know whether it's high priority than other vehicles. It's got to get a set of waypoints. All of these things are things that are better done by the infrastructure, right? The infrastructure knows it has a map. It knows its depot. It knows where everybody should go. It can assign waypoints. There's some funny videos of Waymo vehicles getting in each other's way, trying to find parking slots in parking lots, right? Because they're all acting autonomously, right? There's no central control. So the stuff that infrastructure's better at, we allocate to the infrastructure. The stuff that the vehicle's better at, like, detailed control of how to get to the next waypoint. How do you maneuver when you're in the loading station? When should you do automatic emergency braking? These are things better done by the vehicle itself because it has that detailed knowledge of, its current state. So that's why we are partitioning the work this way in type 3. But as I said, this becomes a system of systems project now where you have different entities working together in a safety critical operation. And that's why these systems of systems projects are more complicated but more optimal. And so in order to deal with a systems of systems challenge, you need a team of teams. So this is our Depot Autonomy total team, which is made up of a bunch of different teams, right? And so Seth is going to take you through that first row there, the software stack that he's creating with his team. Nobilis, who we talked to this morning, is doing orchestrated autonomy. We have a professor doing precise localization with radar. We are creating an open source robotics test platform with a startup called NIFT. Sensors are coming from RoboSense and from 6 Sensors. The communication networks, we're working with U of M Dearborn. Infrastructure investment dynamics, we're working with a professor in civil engineering. The business model, I've been leaning on students in the Ross Business School to do the business modeling for me. And then we have a systems engineering teams, again, student teams doing the architectural framework, working both U of M and Texas A&M. And then we're working with SAE to write it all up in an industrial standard. And so that first bit, the first row is where I invite Seth up, right? He's going to take you through the software stack and tell you some of the details of how it works. Thanks, Seth.
Great. Thanks, Greg. So as Greg mentioned, my name's Seth. I'm a PhD candidate in the robotics department. I'm advised by Professor Katie Skinner and Ram Vasudevan, and I've been working on some of the technical aspects of the Depot Autonomy project. And so Greg talked to you at length about how to make this a viable business case. From our perspective, the problem we're interested in is the technical one, where we are interested in building methods to do perception and motion planning in a depot that is equipped with infrastructure sensing. So if we have a depot with cameras and some LiDAR scattered around, how can we do perception and motion planning? And in particular, how can we do it in a way that provides guarantees, both theoretical and in practice, that all of the robots or all of the vehicles in the depot will behave safely? We want to show that the methods we develop work both in simulation and on hardware with as little sim to real transfer as possible. And sort of in parallel to all of the autonomy work we're doing, one of the things we're going to be able to show is that based on our methods, we can use the techniques we're developing to generate more sensor data, more training data, more scenarios from the ones that we have observed without actually having to build all of the scenarios. And I'll talk a little bit about how we do that. So thinking about robot autonomy, in general, you can put existing approaches to robot autonomy on one big spectrum. So all the way on one end of the spectrum is the fully modularized approach that is most common out in the world right now, where you might have detectors and trackers and predictors and motion planners and optimizers, a whole bunch of components that all have to play nice together. And we have lots of techniques as a community to say that each of these components will behave safely or each of them will result in the correct behavior. But it can be sort of difficult to look at the entire system and provide guarantees that the entire system is safe. All the way on the other end of the spectrum is end-to-end learning methods, what people sometimes call pixel to torque, where inputs are directly mapped to outputs. And it's even harder to certify these systems as safe. And so we like to live somewhere in the middle, developing a 2-module approach where we build one high-fidelity scene representation, and then we have a method for planning and control within it. That's not to say we won't have predictors and trackers and detectors, but we're going to integrate them all into one module where we can do a little bit better of a job certifying the safety. So as I mentioned, we have 2 modules. The first takes an infrastructure sensing. Here we're temporarily operating in a small simulated tent, which mirrors one that we have in hardware up at Mcity. And we build a dense reconstruction. And then we develop a method to do safe motion planning within that representation, and we have guarantees of safety on that planner. So to talk a little bit about the scene representation part of our work, in general, our goal is to input a set of sensor measurements from things like cameras and LiDARs, and we output a model that allows us to predict the probability that some portion of the scene is occupied. So we take in sensors, we use a technique that has sort of taken over the world in the robotics and computer vision space called 3D Gaussian splatting, and it allows us to build a dense reconstruction where we can do things like render what the scene would look like from other views. If you don't know about 3D Gaussian splatting, that's fine. All you need to know for right now is that it decomposes the scene into effectively 1 million plus tiny little ellipsoids, tiny little Gaussian functions. And that allows us to do some pretty cool things with the representation. In particular, we make 2 contributions. The first is we have a method for reconstructing dynamic environments. So typically people build these reconstructions of static environments where everything is in place, leveraging the fact that this Gaussian splatting method estimates the scene as a bunch of little Gaussians. We're able to reconstruct dynamic environments. And then we're able to use the reconstruction to do safe motion planning. One of the preliminary results I'll show you is how we're doing some of that dynamic reconstruction, in particular with people. So if we take in a video of a person, we can use Gaussian splatting to build an articulated 3D model of what the person can do. And so we have this natural video, and then we build an articulated model. There's a couple things this allows us to do. The first is that we actually have some preliminary results to show that by combining tracking with 3D reconstruction, we can get more accurate tracking of people, which can be very useful in a case where you have a lot of different things going on in a warehouse, and you want to make sure that the people are reconstructed accurately. And then we also show that we're able to synthesize new scenes that did never exist in the real world. And so if you look carefully, you'll notice this person is following a totally different trajectory from the one they were in the video. So we've built a model, and now we can reanimate it with a new trajectory. And this will allow us to effectively synthesize scenes that never happened, but in a way that will be very similar to if it did. So from the model's perspective, it's indistinguishable from if the scene actually happened. And this is very useful for generating training data without having to run millions and millions of scenarios in hardware. So the second aspect of our work, which I'll just talk about quickly, is on safe robot motion planning. And so if we have, in this simple 2D example, a forklift trying to make it to some goal with some obstacle, the goal of safe motion planning is always to determine whether or not some path is in collision or whether or not that path is safe. The conventional method is always going to discretize along the trajectory. So here we've taken 3 samples, and it'll check for each sample whether or not that path is safe. The problem is that this leads to a very undesirable trade-off between safety and compute, where you have to decide how many samples do I need in order to be safe enough. And then no matter what, there's always going to be some in-between point where you don't really know what's happening. And then with these models, it's also very hard to do things like account for the dynamics of the vehicle or any uncertainty in the tracking. Our lab over the past decade or so has been working on an alternative where instead of discretizing, we try to build this set that over approximates the volume that the robot might sweep through as it's executing a path. The advantage of this is we have much stronger safety guarantees because we don't discretize, and we can do things like build in localizer error, dynamics tracking error, all sorts of things into these sets. It turns out that at the end, we can then over approximate this set with a bunch of spheres, which makes the motion planning problem convenient. Now we have spheres, and I mentioned that the scene is represented by all those ellipsoids. So now this reduces to a fairly familiar motion planning problem. And so some preliminary results, this is shown in Carla, but it's under the hood using that Gaussian splatting representation, where we're able to avoid both static and dynamic obstacles. And that white set on the ground is our swept volume of the robot might occupy that we've just projected down into 2D. So we have a couple of areas of ongoing work. In addition to the work we've been doing in simulation, we've been working on getting this set up in the real world. So this tent is located up at Mcity and Tree. We're building the trusses, sensors, putting cameras, lidars, compute, everything we need in there. And we're hoping that by the end of the summer, or at the end of the summer, we expect to show a demo of the reconstruction and some preliminary planning results on hardware. In addition to this, the Autonomy team is working on a few further areas of investigation. So the first one is that I showed you that reconstruction that we've built. I mentioned that it can take millions of those tiny little Gaussians to represent the scene. We're looking into hybrids where we can combine the benefits of traditional mesh-based reconstructions like you might see in Carla or Omniverse with the high-fidelity reconstructions we're building. That's just taking advantage of the fact that things like a flat ground plane, we don't need as much fidelity as we might on an articulated human. As I mentioned, we're working on deploying all of this in hardware, and we expect to have results on that by the end of the summer. And then as researchers that work partially in the computer vision space, we are always interested in improving the quality of our reconstructions and just trying to get the planning and reconstruction as high fidelity as we can. That's what I have for you.
Okay, so that's it. We're ready for questions.